Think about the exact moment a principal speaks into a microphone and the hallway music instantly fades away.
Right, it feels instantaneous.
Yeah, but that isn't magic. I mean, it's a $1,400 invisible traffic cop hiding in a tech closet somewhere.
Exactly.
Welcome to today's deep dive, where our mission is to decode the Gain Audio AT-GAIN-M240. We've got a stack of specs for this commercial mixer amplifier, and we're figuring out how a seemingly simple box serves as the hidden backbone of our public spaces.
It really is hidden in plain sight.
It is. I look at this thing and see an audio traffic cop. It organizes, prioritizes, and empowers the sound around you. But directing traffic is one thing. What kind of horsepower are we actually dealing with here?
Well, it packs serious muscle, but the real trick is how it delivers it. There's a mode switch that basically toggles its personality.
Oh, like changing the output.
Yeah. On one hand, it can run as a traditional stereo setup, pushing 2 channels at 120 watts each into like standard 4 8-ohm speakers.
Right.
Or flip that switch and it dumps everything into a single channel, pushing 240 watts at high voltage, specifically 70 or 100 volts.
Okay, let's unpack this. Because 240 watts dumped into a single channel. Wait, if it's pushing that much juice into a standard classroom ceiling speaker, won't it just blow the cone right out of the ceiling?
Oh, for sure. If you use standard 8-ohm speakers, you definitely have a bad time.
I figured.
But that high voltage 70 or 100 volt mode is specifically engineered for daisy chaining. When you step the voltage up, you proportionally lower the current.
Got it.
And that lower current means the audio signal can travel hundreds of feet down a massive school hallway, hitting dozens of connected speakers without losing signal strength due to cable resistance.
So you aren't fighting the friction of the wire. It just scales based on the building's architecture.
Precisely. But, pushing sound down a 300-foot hallway creates a new physics problem, the speed of sound.
Wait, how so?
Well, if someone is standing near a speaker at the end of the hall, they'll hear that speaker instantly. But the sound from the speaker 50 feet away will hit them a fraction of a second later.
Oh, wow.
Yeah, it creates this muddy, echoing mess.
Which means pumping out raw power isn't enough.
Right.
It has to know how to time the delivery.
Exactly. Which brings us to its brain. The unit has built-in digital signal processing, or DSP.
All right.
It takes in up to 4 analog inputs, like microphones or line-level audio, and lets you apply a physical delay to the signal. You literally dial in the timing, so every speaker in a massive space hits the listener's ear at the exact same millisecond.
See, here's where it gets really interesting. There's a feature in this DSP called ducking.
Oh, yeah, the ducking is crucial.
I like to think of this as a hyper-aware party guest. The person who instantly turns down the stereo the exact second someone picks up a microphone to make a toast.
That's a great analogy.
But how does the box actually know to do that without a sound guy pushing a fader?
It's all about thresholds. The DSP uses the incoming microphone signal as a trigger. The moment the voltage from the mic hits a specific volume threshold you've set, the amplifier's brain automatically squashes the gain on the background music channel.
And then brings it back up.
Yeah, when the voice stops, the music just swells back up. But what's fascinating here is how this ties directly into accessibility.
Really? How so?
The unit has independent mixes. That means the main amplifier and the line-level outputs can have completely different volumes.
Oh, okay.
By feeding a balance line output directly into a facility's assistive listening system, that automated ducking ensures deaf or hard-of-hearing individuals get a perfectly prioritized announcement beamed right to their devices.
Wow, without the background music bleeding over.
Exactly.
So it's actively solving accessibility problems.
Yeah.
But taking a step back, this is running in schools, retail stores, huge buildings. How does a beefy 240-watt brain fit into modern energy-conscious designs? I'm picturing a massive hot server rack.
Actually, it's a 1U half-rack enclosure.
Wait, really?
Yeah, it's tiny, about half the width of a standard server slot. And they managed to build the power supply directly inside, so there's no bulky external power brick to hide.
Oh, that's nice.
Plus, the unit features LAN and RS-232 interfaces.
So what does this all mean? Does RS-232 just mean it speaks the same digital language as the building's central computer?
That's the exact functional benefit, yeah. It means the lighting, the HVAC, and the audio can all be managed together.
Okay.
But it also thinks for itself. It has an auto standby mode configurable from 1 to 1,440 minutes.
So it puts itself to sleep.
Exactly. If no audio signal passes through for that set time, the amp shuts down its thirsty power stages. On the network, it drops to a 2-watt draw. If it's totally idle, it sips just half a watt.
Which means the IT manager doesn't have to walk around the campus manually shutting down audio racks every night.
Right, and if we connect this to the bigger picture, commercial buildings bleed money on vampire power devices left on overnight. Automating that standby process removes human error entirely from the commercial energy waste equation.
That makes so much sense. So the AT-GAIN-M240 isn't just a basic amplifier. It is a highly automated, energy-efficient audio management system disguised as a simple little 1U box.
Yeah, it takes complex signal routing, acoustic physics, and power management, and just makes it all completely invisible to the end user.
Well, the next time you hear a perfectly timed, crystal-clear announcement in a sprawling store or a school, consider the invisible, automated decisions happening inside the walls. Our audio traffic cop is always on duty. It makes you wonder how much of our physical environment is secretly reacting to us, measuring our inputs without us ever noticing.